Hi, this is Young-Soo Chang from KAIST, and I will be presenting our work on Monte-Carlo Planning and Learning with Language Action Value Estimates, which is showing effective exploration in natural language action spaces for interactive fiction games. This work was done jointly with Seok-in Seo, Jong-min Lee, and Ki-young Kim. Exploration is one of the key challenges of reinforcement learning, especially in large action space and sparse reward environments. Recently, there have been many approaches to effectively explore the action spaces, but it still struggles in the natural language action space environments such as interactive fiction games. IF games have a large branching factor. It renders naive exhaustive search invisible and lays the strong need for language-grounded planning ability. Unlike ordinary discrete actions that are considered as independent discrete tokens, natural language actions are closely related to each other. So it needs to incorporate natural language understanding into exploration strategy in order to assign non-uniform search priority. Our work is based on the Monte-Carlo tree search framework. UCT is the standard MCTS method, which adopts uncertainty-driven exploration, and PUCT partially incorporates prior knowledge into search as a policy, but it still lacks language-grounded planning ability. In this work, we introduce Monte-Carlo planning with language action value estimates, MC-LAVE, which combines Monte-Carlo tree search with language-driven exploration. Our goal is to share the information between language actions based on their semantic similarities. First, we define the semantic neighborhood by cosine distance in embedding spaces. Then, in order to encourage optimistic exploration, LAVE exploration bonus is estimated through a soft maximum over the Q values of actions in semantic neighborhood. This language-driven exploration allows a more focused exploration on semantically promising actions, but it does not hurt the asymptotic behavior of MCTS, which we formally show in the paper. Similar to AlphaZero, we use MC-LAVE as a policy improvement operator for running the policy. First, we use MC-LAVE to collect the planning trajectories and transition tuples. Then we can train the policy with behavior cloning and Q-network with minimizing temporal difference error. And we can perform the MC-LAVE again with trained policy and Q-network. We continue this policy iteration with MC-LAVE operator until the policy performance converges. Our experiments were conducted in IF games included in the Jericho environment. This is an example of observation and action from Group 1, which is the most representative IF game. IF games are fully text-based environments where the observation and the action spaces are defined as natural language. We compared the performance of MC-LAVE-RL with the baseline algorithms. This table summarizes handicaps leveraged in each algorithm and the performance of each algorithm. Although MC-LAVE-RL requires more handicap or assumption, it outperforms or matches the state-of-the-art results on most games. These are illustrative examples of the behavior of each agent playing Jork 1. In Jork 1, a human player would be naturally capable of performing strategic planning, through language understanding and common sense listening, such as take a lantern should precede entering the dark cellar. However, most of the baseline agents except MCQBert just enter the dark cellar without lantern to obtain an immediate reward, then only discover a few states. However, with language-driven exploration, MC-LAVE-RL enters the cellar by taking lantern, then discovers more noble states than others. An explanation of the contents of our paper ends here. From now on, I will briefly explain how to run our code. Our code is publicly available on GitHub, and you can download it from this link. To run the code, you need to set up the environment first. You can just set up the environment through Anaconda in the following order. All experience in our paper were conducted with Google Cloud Platform and HT Condor to run in parallel. For time efficiency, it is highly recommended to use environments that enable parallel processing. Our code is roughly structured as follows. The first folder is the code for the Jericho environment, which is the experimental domain of our paper. Codes corresponding to the core part of our algorithms, such as MCTS, policy network, and Q network, are implemented in SRC, and the three codes below are used in actual execution. Our algorithm first collects MCTS planning trajectories through runPlanning.py code. Since all the planning processes are performed independently, they can be processed in parallel and at the same time. After that, mergeplans.py is executed for the process of merging the collected data. The following figure is an example showing how the planning result trajectory is actually selected based on Q value and vegetation count through runPlanning.py code. Through this, you can check the criteria on which the actions of the planning trajectories were selected. And by using the data collected through this planning, Q network and policy network are trained. You can train the Q network and policy network by adjusting the mode of the running.py code to 0 and 1 in the process. The process up to this point corresponds to policy iteration, and you can carry out this process until the performance of the policy converges. This is the end of my presentation. Thank you.